Hopi Lake. If you look at the shaded relief map of North America and you see that basin right there, topographic basin, a structural basin that's 300 kilometers long. It's about the length of Lake Michigan. And it's the size of Lake Michigan. About 1,000 cubic miles of water could fit in that basin if it wasn't for the Grand Canyon being there on the western side, of course. Okay? Could Hopi Lake Basin have been filled with Hopi Lake? Okay, it's called Bidahochi Basin. It's a terrain model. Here you can see a simulated lake model. The lake is filling through about 5,800 feet elevation, and as it's filling, it is up against Grand Canyon. See Grand Canyon right there and the Kaibab upward. So this huge lake, 300 kilometers long, could have formed, and that's the possibility we want to consider. The fly through of the basin. You can see this long basin. And then up against the basin at 5,800 feet, the lake could have existed. I believe the lake existed at 6,100 feet elevation, but you can see Eastern Grand Canyon there in the terrain model. That's a simulated terrain model by Nate Loper. What do transgressive shoreline terraces look like? We have a wonderful example in Utah. In southern and central Utah, you've got Lake Bonneville Basin, and Lake Bonneville filled rapidly and progressively to spill at the Lake Bonneville shoreline about 5,050 feet here, and it created the shoreline terraces. Do you see that? Isn't that interesting? Transgressive shoreline terraces by the continual filling of Lake Bonneville and then the catastrophic flood lowering of Lake Bonneville. That's the idea that we have for the origin of shoreline terraces on Hopi Lake. And you see this? The shoreline terraces are there on the side of the volcano, the basalt volcano. And then, but notice this, the top of the volcano at low slope doesn't show the transgressive shoreline terraces as well, and but they're there. Here's the brown knoll. If I push the button, look at this. Okay, you can see as we overfly it that you can get a three-dimensionality of the shoreline transgressive terraces. And notice that the top of at low slope about 0.02, 1 to 50, something like that, the shoreline transgressive terraces disappear. So they're weakly developed. And you might ask, would you even expect to find shoreline terraces of ancient Hopi Lake on the low slope angles around Bidahochi Basin? Bidahochi Basin shoreline is low angle. Was Bidahochi Basin the holding pond of ancient Hopi Lake? That's the proposition. And do shoreline terraces exist from Hopi Lake, like those transgressive shoreline terraces from Lake Bonneville, the Ice Age lake in Utah? Here's the overview. Let's look at the 160-year or 165-year legacy of Hopi Lake. I'm going to talk about that legacy. It's remarkable and very interesting, and that could be a subject of a whole lecture. Basin structure and stratigraphy. I'm going to talk about Bidahochi Basin stratigraphy. Then the 25 square kilometer research tract of land. And then I want to talk about landforms at 1,700 feet elevation, 5,740 feet. And then landform interpretation options. I'll give you some options, 5 different options. I think the explanation is landforms are shoreline terraces. And then we want to do a top-down spillover failure model for how Hopi Lake may have failed to form Grand Canyon. That's a lot to do. Okay, John Strong Newberry, an amazing story. The first geologist to explore Grand Canyon, 11 years before John Leslie Powell went through Grand Canyon in the on the river in his boats. Newberry explored Grand Canyon at Diamond Creek, April. He spent 5 days, April 1858. He walked completely across Bidahochi Basin to the east of Grand Canyon. Then he measured the thickness of the Bidahochi Formation before it was even recognized as the Bidahochi Formation, but he measured the thickness of the sedimentary deposit before it was named Bidahochi, and then he recognized that there was an ancient lake there. Okay, so he did all of the logical links to think about this, and so the first geologist thought in terms of what I would call, he published the idea of spillover drainage eroding Grand Canyon. Isn't that interesting? In 1861. Something happened right after that was bad news. There was a civil war, and the main contractor he was working with was Lieutenant Eves on his expedition, and Eves joined the South, and he was a traitor, and of course Newberry's explanation faded into oblivion, okay? And it's people like us that have rediscovered it. Okay, so Hopi Lake's legacy began with John Newberry, 1858, and Hopi Lake was finally named Hopi Lake by Howell Williams in 1936, and the name Bidahochi Formation was a little bit earlier, but Bidahochi Basin began to be named and described as under that term by the 1980s. So what would you say? Hopi Lake gets no respect. It's a Rodney Dangerfield. It don't get no respect. Okay. And so basins aren't looked at geologically like mountains are. Mountains are looked at with awe and dignity, but basins don't get no respect. The Little Colorado River occupies nearly the bottom of the synclinal trough or basin of which the mountains I have encountered form the rim of the southern half. And Newberry's comment on the basin, which later became called Bidahochi Basin. Anyway, he recognized it as a synclinal trough, and the mountains he encountered on the southern half, that's this area right here, that's the Mukion Rim, and then here's the basin, there's the Hopi Buttes volcanics, and the Bidahochi Formation that he described. There's the Bidahochi Formation, beautiful, hundreds of feet of lake sediment that he understood. He measured the thickness of the lake beds in 1858. Okay, Reagan is the fellow that named the Bidahochi Formation in 1924, and it wasn't until Hopi Lake was established by Howell Williams describing the volcanics in the Hopi Butte area in 1936. So the terminology even describing this was rather lately developed. And of course, at that time, of course, John Wesley Powell and the idea of geologic time ascended to what? Dominance, okay, as Hopi Lake got no respect, and geologic time and what? The Colorado River made Grand Canyon over millions of years. You know the rest of that story, right? Okay, let's look at this area, and I'll talk about that and we'll the authors of our paper, we've investigated that area right there, the 25 square kilometer area. But you see the massiveness of the basin, and you see its relationship to Grand Canyon. Here's what he said. Whoop, missed that. Doubtless, in earlier times, Colorado River, filled these basins to the brim. Its accumulated waters poured over the lowest points, and the barriers which oppose their progress toward the sea have cut them down from summit to base, forming that remarkable series of deep and narrow canyons, leaving open areas which once lakes and afterwards fertile valleys, now arid and sterile wastes. And so obviously in the writing of John Strong Newberry, there's this amazing legacy of the spillover idea. And it's all right there in the first geologist who explored Grand Canyon. Our field research area is that little area, limestone ramp. You look at this area, limestone ramp, and there is a Grand Canyon over there. The details, it's near Meteor Crater, 18 miles or so, 18 kilometers northwest of Meteor Crater, right here. It's along Interstate Highway 40, about an hour east of Flagstaff, Arizona, along Canyon Diablo, which is a tributary to the Little Colorado River, and Yellow Jacket Canyon, Wagon Box Draw, and Anderson Canyon. Those are the primary geographic features, and I'll center on Wagon Box Draw. But you see its relationship to the Mogollon Rim, the structural basin, and those slopes in there are 1 to 50 kind of slopes. 1 degree angle, sometimes 2 degree angles, but not steep angles like 5 degrees or something. And there's the topographic map of the area, the 25 square kilometer area. You see within the topographic map the 1 mile grid sections that describe the survey. And you see the location of the interstate highway, and it's south of Interstate Highway 40 at exit 225. Billingsley just recently published the geologic map of that area, and notice that the limestone ramp has a dipping slope to the northeast, and that limestone ramp with a dip slope to the northeast is dominantly that blue geologic formation, and that's the Kaibab, and the upper Kaibab formation is called the Harrisburg member, and that's the unit that outcrops along there. Notice the northeast plunging gentle folds. There's the northeast folds. Those are anticline, syncline. They're very gentle folds, but they're trending to the northeast along with the ramp. And then one of those anticlines comes across the structure and dives off to the north. And that's interesting, and we can talk about that as well. But anyway, you see the northeast plunging gentle folds, and then the northwest trending Listric fault. There's a Listric fault, Listric fault means curving down and flattening with depth. That's largely pull apart, and that could be related to the tectonics of forming the ramp. But the listric normal faults are divided into northwest trending. The northwest trending listric faults are into northwest trending grobens, and there's the groben structure running through the center of the area. And so you can see all kinds of interesting geologic features, and the geologic map shows us those. 5 locations around the area are where we have outliers of Moenkopi. See, Moenkopi sits on top of Kaibab, and Moenkopi, big Moenkopi outcrop right there in that area. Down here, there's a Moenkopi outcrop, and up there north is a very excellent Moenkopi outcrop. So anyway, the Moenkopi formations are there, and you see that on the satellite photo. Invisible, essentially, in many places. There's a little bit of Moenkopi sitting there. There's the Graben structure with Moenkopi in it. Here's a Moenkopi outlier, there's a Moenkopi outlier, and there's Moenkopi down there. So what we're looking at is a ramp, okay, a northeast dipping ramp. On top of it, the dip slope of the ramp are these outliers of Moenkopi. And so you can see where the Moenkopi sits on top of the Kaibab, and the Kaibab upper formation, upper part is the Harrisburg member, and there's the lower part of the Kaibab, that's the Fossil Mountain member. And so you've got these 2 members of the Kaibab overlain by the Moenkopi. Now the limestone platform unit is the upper 7 meters or so of this Harrisburg member of the Kaibab, and that's what we see outcropping in our limestone dip slope ramp. So here we are, limestone Moenkopi outlier, probably not limestone Moenkopi, it's limestone, it's siltstone Moenkopi. So you have siltstone overlaying limestone. So the Moenkopi is distinctively different than the underlying Kaibab, especially the Harrisburg member, and that limestone platform unit would be right underneath that Moenkopi. There it is. You see the limestone, or the Moenkopi outlier over the Harrisburg member of the of the Kaibab, and that's that platform unit. And you can convince yourself that that slope is the upper part of the limestone platform unit, and it goes up to that Graben structure right there with listric normal faults. And on the other side of that listric normal fault, on the other side of the Graben, is the fault scarp, very obvious fault scarp with the platform unit on the other side. So we'll fly into that and look at that, and then we'll get even closer. Platform unit, uppermost Harrisburg member right here. There's the fault, okay? There's the Graben, and there's the other fault. A pair of faults make the Graben, and there's the scarp, and there's the hill on the other side. We call it Nate's Hill, in honor of Nate. It doesn't have a name, so you can name it after your co-author or something. Okay, there's Nate's Hill, and you can see right there, the next photograph shows it. Look at this, limestone platform unit on Nate's Hill, okay? And you can see the individual strata of limestone in the fault scarp of the dip slope that forms Nate's Hill. You see that? And then what is that, okay? See that? That's really interesting. What are these linear landforms doing on this limestone dip slope at 5,740 feet elevation? What are they doing there? Here's a video. Those individual shrubs, bushes there, are about 1/2 meter in diameter. So these landforms have a spacing of about 20 meters over the ground. You see that? And we got fascinated by the linearity of these ridges, especially with the low fillings in between. Landforms at 5,740 feet. There's the fault scarp. There's the fault scarp. Now, we see from high angle in this unmanned aerial clip. Now, here you see it low angle. Overflight. Each of those is about 20 meters. That's 20 meters distance, something like that. And so you can see these linear landforms. What do they represent? Are these shoreline terraces of ancient Hopi Lake? There's up against the fault scarp again, looking kind of northward there, and you see these, and they're on the dip slope. The slope is up to the left there. Interesting, isn't it? Okay, so we got interested in that. We designated 25 square kilometer area, and Ed Holroyd especially stitched together the available satellite photography, and he composed a 25 square kilometer area composite image with about 1/2 meter resolution. So that means there's something like what? 100 million pixel image of that terrain. And you can look at it and get fascinated, but we designated 13 areas in the terrain there that were most interesting, and I'll talk about just 4. There's Interstate Highway Arch. See the interstate highway, and there's that anticlinal arch that goes through there. That's called Interstate Highway Arch, and you can even see at this resolution, there's a quarry there where they quarried the gravel at the surface. Then there's Chevron Hill, and it's a top of a hill with that broad arch structure. Then down south is Nate's Hill. Nate's Hill is dip slope, and then down here is what we call Graben Hill. And on the satellite photograph, we have 2 meter interval DEM, digital elevation model from USGS that's superimposed on that. So we have a very detailed topographic contour. And that's the purple lines are the original 40 or 20-foot contours of the USGS map. And they agree with the DEM in an excellent way. Interstate Highway Arch. There you can see the quarry site. look at the quarry site where they quarried the gravel off, you can see even more vividly the structure of the linearity. And so what's going on with these linear features wrapping around the nose of that anticline? That's kind of interesting. And then if you think about it, they follow contour, don't they? Okay, generally follow contour, and I'll talk about the contour following. There's Chevron Hill, and Chevron Hill is the top of that hill and very topographically elevated, yet you see these linear features here. And down here is the Graben. There's Nate's Hill. Nate's Hill is a dip slope, and we see it there. What's interesting is we followed one, what appears to be crest line of a terrace, a shoreline terrace, we assume, about 1 kilometer along the slope, and it didn't cross any of the DEM 2-meter contour interval. So it's essentially level for 1 kilometer. Then you notice something. What happens here is they deviate from the level of the contour, and they dive down. What's going on there? It's up against the fault scarp, and that is drag on the fault scarp. In other words, the landforms are affected by the tectonics of the fault drag, and that argues that the landforms are older than the cross-cutting listric faults that form the Graben structure. Interesting, isn't it? So the deviations from horizontality of the structures seem to correspond to the structures in a rather coherent way. And then Graben Hill is the same story. On the other side of the Graben, you can see the linear features, especially away from the Graben, but as you approach the Graben fault, they also deviate from horizontality. So, and there's the Graben right there. And so this whole thing is rather interesting. First of all, the elephant in the room. Okay, you wanna talk about the elephant first, right? Okay. What do you see as you're just out there on the landscape? What do you see? Well, it's kind of interesting and subtle, but everything is encrusted with this kind of yellowish brown, couple centimeter thick crust, which we would normally call tufa. And if you know anything about tufa is a prominent feature of a shoreline. So tufa and shorelines go together. And so as we're seeing tufa, we think, oh, could it be beach and beach erosion feature? And then as you're looking at this thing, I see, look, a whole bunch of blade-like clasts and tablet-like clasts that don't roll easily, and spindle-like clasts, long pencil-like things are gonna roll away, and those aren't very common, but the tablets and the slabs, the tabular slabs are very common. So that's what you see on a beach, right? Tablet-like slabs, oblate clasts. And then when you see a beach or a terrace-like thing, you think of, upslope, and you think, there's an eroded place, and there's an erosional divot, and then of course you see flat country, and so there's a bedrock high, and you can imagine erosion against the bedrock high. The elephant in the room would be beach, right? So beach deposit. And what we would like to point out is that you see this face feature, looks like an eroded shoreline deep facing the the water line, and then above that is this elevated berm, and then in back of that is the flat. And the next flat, and then the next structure. So you find yourself saying things like, beach, okay? There's the coating, the normal color of the Harrisburg member of the Kaibab Formation is what? Gray, and is covered with this coating of that centimeter thick, kind of yellowish brown feature, and it's a couple centimeters thick, and it's porous, it is tabular, it has a layered lamination to it a little bit, and it's botryoidal masses that seem to be growing. You can see that in the flashlight microscope, looking down into the holes. I like looking at tufa, seeing the holes and looking in the holes. That's and so you're seeing silt-sized particles that are cemented by microcrystalline calcite. And there's the silt-sized calcite, 100 micron grains here, and there's a 1 millimeter long hole. It reminds us of the Bonneville shoreline capping tufas along the transgressive shorelines of Lake Bonneville. Okay, the elephant in the room again. Okay, and Lake Bonneville tufa is rather thick. It's not 2 meters thick, or 2 centimeters thick. It's many centimeters thick. And so tufa is a primary shoreline feature of Lake Bonneville. Again, looking at the flat, the berm, the face, and the flat. The flat is composed of soil development and aeolian and alluvial debris that's accumulated in the flat areas between these bedrock ridges, and the berm and face show the feature. There you go, berm, flat, face, berm, flat, and then another face and another berm, and you see the progressive structure of the thing. So looking up slope, flat, face, berm, flat, face, berm, you can see them back there. That's the linear features. Okay, what do you see looking downslope? It's a very interesting and provocative thing you see looking downslope. What do you see? Basically nothing. Okay, why? Because the face of the landform is oriented down slope, facing down slope, and that shows you the clip of the landform is there. Okay, landform interpretive options, pattern from multiple flatline outcropping strata, that's a possibility. Pattern from erosion of strata with strong joining expression, we've considered that possibility. Then we are thinking about pattern from erosion of dunes or boudinage in the stratum. For example, a dune-like feature in the upper part of that limestone platform unit of the Harrisburg member. And how about this one? Pattern from soil solifluction and gravity collapse, or gravity compaction. Starting to think about those kind of features. Well, okay, or what? The obvious possibility, transgressive depositional terrace of Hopi Lake. Okay, those are the 5 interpretive options that we see, that we think about. How about joints? Well, there's the fault scarp along the Graben, and you see the joints are parallel to the faults, the listric faults, not parallel to the landforms. So you can kind of rule that one out. Look at this, joints are not expressing themselves in a landform way, in big way. And then the boudinage idea that there's some type of layered feature there, yeah. And dune-like progression, that's what's obvious boudinage. Could the boudinage be an expression? But think about it. If boudinage is the structural reason why the landforms are there in the upper part of the limestone, then the limestone hummocks have to coincide with the present topographic situation. And that's weird, okay? And so, and thinking about gravity, compaction, and some type of solifluction process is also seems extreme. So we find ourselves asking all kinds of questions. Notice no boudinage structure in the upper part of the Harrisburg member of Kaidap limestone, right there with Moen Hopi on top of it. Yeah, so those alternate models are really stretching it. So evidence for Hopi Lake terraces. Strong horizontality of landforms, especially on bedrock dip slopes, like Nate's Hill here. Deviation from horizontal explained by tectonics, like the landforms deviate from horizontal around the fault scarps because the landforms are older than the fault scarp and the drag features that are formed. And strong association with 1,750 meter elevation, 5,740 feet elevation. The landforms appear to be beveled horizontally into the slope with common tabular class as beach features. And then contains capping tufa resembling the Lake Bonneville tufa, and it resembles the stair-stepping transgression of Lake Bonneville depositional terraces. Is there any other thing that we need to provide for an argument that these are shoreline terraces? Are you with me? Here's my model. Here's our models. We've talked about it. You have 25-fold vertical exaggeration. You got the dip slope of the limestone with resistant and friable beds, and you have the lake advancing rather rapidly over the dip slope. And at shoreline S1, the shoreline velocity depth profile, you have higher velocity in shallower water. So as the lake advances over this slope, it eats first into the gravel platform, makes a gravel covered, erodes a flat platform. Then as the lake gets deeper, it erodes the erosional scarp, which becomes the face of the landform. And then it keeps eroding back, but it can't erode deeper because of the resistant stratum underneath. So it goes back to building these transgressive depositional terraces. So we call this the transgressive depositional terrace model because gravel covered platforms are left.
Why not numbering in a different way from regression?
Okay, let me finish up here. The linear ridge, horizontal landforms, dip slope are transgressive shoreline depositional terraces from rapid filling of ancient Hopi Lake. You see the transgressive shorelines, rapid filling, but there's no regressive shoreline. Why? Because the lake disappeared rather rapidly, gone. Okay, but it left a transgressive shoreline terrace record. So Hopi Lake holds water. How's that? Let's consider the spillover model. Here's, and I've got a couple minutes here just to do the shoreline model. But Bidahochi Basin was originally vacant of a big lake, I believe. And we have the lower Bidahochi Formation, which argues that it wasn't a deep lake at the time. The lower part of the Bidahochi was deposited. The upper Bidahochi has the deep basin siltstones and clay in it. The upstream basin structure failed from top down. And the top-down basin failure model is currently the favored model among spillover people who think that spillover is very active in understanding landscapes. But the fail from the top down. That means that lakes upstream of Hopi Lake failed first, then they failed into Hopi Basin. So Canyonlands Lake fails into Bidahochi Basin, which is largely vacant of a lake. Are you following what I'm doing here? Okay, and then Bidahochi Basin fills progressively, rather rapidly, and then Hopi Lake fills to final elevation. I believe it's about 6,100 feet elevation, and as it fills, then it fails by spillover. And when a natural dam fails in spillover, it fails rapidly. There's no such thing as slow dam failure. You talk to engineers about that. Okay, and spillover erosion of Grand Canyon begins as a spillway is developed from the overtopping and spillover of Kaibab upward. So the Hopi Lake fails by spillover the Kaibab upward, eroding a spillway, and then that fills the next basin downstream, right from the top-down basin model. So filling of Lake Toroweap at 5,800 feet occurs, and then Lake Toroweap off to the west down that area, central Grand Canyon, it fails by spillover at Toroweap Point, and then the basins continue to deepen as the failures downstream continue to occur. You got the model? Okay, now we can illustrate this by, there's Canyonlands Lake in Utah, there's Paria Plateau, Kaibito Plateau, spills over there at Lee's Ferry, spills into the upper part of Bidahochi Basin, which is separated by Blue Moon Bench, that's over top, then the lower part of Bidahochi Basin fills, and you form Hopi Lake, right? And then Hopi Lake overtops, and it erodes a spillway through the Kaibab upwarp, and then once it gets off the upwarp, it ponds into the next terrain lowland basin there, which is Toroweap Basin, and Lake Toroweap was formed, and then that basin breaches, and those lakes drain, and as those lakes drain, and Hopi Lake continues to drain, then it leaves behind Grand Canyon. You like something like that? That's our model for formation of Grand Canyon by Hopi Lake spillover. Here's our conclusions. Hopi Lake legend, or the Hopi Lake legend lives. It's got extreme explanatory power, doesn't it? And evolutionists have tried to kill it. Everybody's tried to kill it, but it's still alive and well. Okay, landforms are shoreline transgressive depositional terraces. The terraces conform to the old slope of the basin ramp. They deviate from the basin ramp by drag-on faults. Transgressive Tufa-Encrusted landforms indicate rapid filling and failure of Hopi Lake. And then the top-down spillover model explains erosion of Grand Canyon. Thank you.